enough for anything. But today we're going to finish the 3D joints. We'll do an example, and then I can assign some stuff over the weekend. And then we'll finally be ready for your first weekly assignment.
We haven't had weeklies in statics?
No, not a single one yet. Okay, so now we're going to get into the pin joints. And we're starting with joint category 4. And this is a little bit of a tricky one. Okay, so joint category 4. This applies 2 force components and 2 couple components. Okay, and so that means that it introduces 4 variables into Newton's laws. And what else was I always saying? That it eliminates, 4 degrees of freedom. So it eliminates 2 translational degrees of freedom and 2 rotational degrees of freedom. And there's only one of these. And it is a pin joint without thrust. And what is thrust? Thrust is a force along the axis of rotation. Okay, so I'm going to try to draw this. So let's say we have one body like this. Man, I'm bummed out. I used to have a 3D printed one of these, and it made it so much easier to explain what was going on, but somehow I lost it. Okay, so there's a pin joint without thrust. Let's say this is body 1 and this is body 2. And I've drawn that axis as really long, and I've drawn those so that they're not touching each other. They're only touching the axis. I've tried to make that really explicit in that picture. And so the idea there is that these 2 bodies have some room to slide along the axis. Okay, so there's no force restricting their motion along that axis. The axis being long and those 2 things being separated like that has the effect of not applying thrust. Okay, because they can just slide freely. Remember that forces and couples are only applied when they eliminate motion. So if this motion along the axis is allowed, there's no force there. Okay. And so I'm going to draw a free body diagram of body 1. And it looks like, so there's the body. So this body, think about what, so imagine this two being fixed or whatever. Think about what motions are eliminated by this joint, okay? Can this thing move, let's say the x-axis is sort of this way. So can this thing move at the point of contact along the x-axis? No. Perpendicular to that, can it move along the y-axis? No. Can it move along the z-axis? Yes, that's because there's no thrust provided, okay? And now think about rotations. Well, one rotation is definitely allowed along the axis, okay? But now think about, like, what about a rotation about what I'm thinking of as the y-axis? That would be like a twisting of this thing, sort of. Is that allowed? No. And then the second one is side to side. Is that allowed?
No.
No. And so that shows you the two couples that are provided and the two forces that are provided. So the way we're going to show this is, so here is the y-axis, and we're going to have like a, we're going to have an ry. I'm going to give myself a little more space here. And then we said that rotation about y isn't allowed. So here's how we're going to show couples. So we're going to also show this as a vector component, and I'm going to do the two arrows to indicate that that's a couple vector, not a force vector. Think of like the two arrows as indicating the two forces of the couple. Okay, so and we'll call this my. And then perpendicular to that along the x-axis. So these are perpendicular. Whoop. We have a force vector this way. That's Fx. And a couple vector this way. That's Mx. And then you could also write these with the subscript notations. F12x, F12y. I'm going to make this F, not R, just so it's the same vector. Sorry about that. Okay, so those are the four loads that joint applies. And if you went to body 2, those would be equal and opposite. There's one important thing about this, and we're going to see this in pin joints with thrust too. And that is often when you have multiple pin joints in 3 dimensions, when you have pin joints in 3 dimensions, you have multiple ones sort of serving the same purpose, allowing motion along the same axis. And when that happens, you don't include those two couples. You only include the forces. And I'll try to explain why that is. But don't include the two couples the two couple components when two pin joints act along the same axis, share an axis. Okay, so I have a pin joint here. So let's think about this pin joint first. And so this one, this one provides thrust because these two things can't move relative to each other along the axis. But everything else works the same as the one I've drawn. So if you try to twist this, it doesn't allow it. That's one of those couples. And if you try to move it side to side, that's not allowed. So it applies a couple on that axis. But notice that, like, if you wanted to break this thing, the way you would break it is by exactly trying to apply to try to move it along those two rotation. You know what I mean? You'd twist it and you'd bend it side to side, and pretty quickly you would break this thing, right? So a single joint, pin joint like this, is not very good at applying those couples, okay? It does it, but it only does it until it breaks or deforms beyond what it was supposed to be, you know? And so for engineering purposes, you get a lot better behavior, a lot stronger joints if you put two of these together to serve the same purpose. And when that happens, so like the hinges in a door, you know, okay, so, well, here we have 4 of them, but you can imagine, like, mathematically, a single hinge would do what we want, right? But pretty quickly, the weight of the door would just bend that and break it, right? So you put another one that allows that motion along the same axis, and now instead of that individual joint having to apply the couple, remember, a couple is just 2 equal and opposite forces, okay? Now, this one can apply a force in one direction, this one can apply a force in the other direction, and without the joint itself applying a couple, the two together have the ability to function as a couple, okay? So, in other words, in the case where you have a hinge here and a hinge here, you don't have to treat this, like, this joint doesn't have to provide its own couple. The two together with their forces produce the couple that's needed, and it's much stronger that way. And so I think the first example we're gonna do, nope, it's not. But let me draw a picture of what this would look like. So if you had a plate like this, and it was attached to the wall with a hinge here and a hinge here, then this is a case where when you drew the free body diagram of that plate, it would only apply forces like this. I'll call this R1X, R1Y, and forces like this, R2X, R2Y. Because those two are acting along the same axis, we wouldn't put the couples in there. Okay? Yep.
Assuming that it might slide.
Yeah, this is assuming that that plate can slide. Yep. Any other questions?
If we, assuming it is not sliding, we would add that couple.
Not the couple. The sliding is provided by the thrust, and we'll put that, that'll be the one in joint category 5. So it's just going to add one more force. Okay. Because it's that sliding is a translation, so it has to be a force. Okay. Any other questions? Okay, joint category 5. We're almost done. How do we know that we're almost done? We only have 6. There's only 6 degrees of freedom you can get rid of. So joint category 5. This applies 3 force components and 2 couple components. And that means that it eliminates uh, 3 translational degrees of freedom and 2 rotational degrees of freedom. Bless you. And it introduces 5 variables into Newton's laws. Okay, that's enough. It's not all about you. Okay, so the one here is a pin or a hinge joint with thrust. And so this is one with thrust. Like I said, you can't slide these relative to each other along the axis. And so usually the way thrust is eliminated in a joint is with some kind of flanges on the sides that keep it from moving. So again, bear with me while I try to draw this thing. So you'd have something like this, and then the body, and then a flange on the other side. Not bad. So this, we'll call that body 1. And so now think about the degrees of freedom that are eliminated by this joint. This can't translate up or out. So those are 2 force components. This time it also can't translate along the axis. So that's the 3rd force component. Okay. In other words, that point that's connected to the pin can't go anywhere. All of its degrees of freedom translationally are stopped. And now think about rotations. It's prevented from twisting. So that's 1 couple component. It's prevented from doing this. So that's a 2nd couple component. It's not prevented from doing this. So there's only 2 components of a couple. And so the free body diagram here so we would have a force this way, I'll call that Rx. A force this way, call that Ry. A force this way, I'll call that Rz. And now the couples. Oh, I drew this one too close. Okay, so now the couples, we have one this way. That's Mx. And one this way. That's My. Usually, instead of drawing all 3 of those force components variables separately, I'll do it like this. So we have the body. We have a full force vector there. So I'm just going to call that the R vector. That has 3 components. and then the couple components, mx and my. Yes.
For those like sort of Christmas tree arrows,
Yeah.
The moment that they're restricting, we get from the right hand rule of like their direction.
The direction, you just always draw them in the direction of the positive axis.
Okay.
But you're right that if you get a positive value of this, the rotation is determined by the right hand rule.
Yeah, so it rotates around the Christmas tree, not like
Right.
for that X arrow it would be like
Exactly.
this way.
Yep. And that's something you're going to just have to get used to for all rotational quantities. The rotational quantity is like the vector component is your thumb, but the rotation is from the right hand rule. Yep. And with this one, same thing as before. This is an important fact about these, like the door hinges thing. If you have two, I'm going to say two coaxial pin joints that share an axis. Then you don't include those couples. So like, for example, let me draw the same thing again. Let's say we have a plate and there's a hinge over here and a hinge over here. And let's say that this one provides thrust. And this one provides no thrust. Okay. Then a free body diagram of this would look like, there's the body. The one with thrust would look like this. So there's a full unknown force vector. I'll call that R1. And then there's two, these share an axis. So there's no couples on this. Okay. And then over here, this one has no thrust. So all we have is R2X, R2Y. And in problems, they're never both going to have thrust included, because then you'd have, for your, in this case, like for your Z component of Newton's second law, you'd have two unknowns and there'd be no way to get to those. It would be statically indeterminate. Okay, so with stuff like this, at most there's going to be one of these two joints sharing an axis that has thrust. Okay, and now the easy one, joint category 6. So this is, yes?
For category 5, we don't draw the moment on those two vectors, but there is, like, they're going to generate a moment together if we try to rotate it. Right?
Correct. Yep.
So would we just like draw it in the center? Or...
No, so what happens is when you use Newton's laws and you say that this is statically, that it's in static equilibrium, this allows you to calculate what the forces are that provide that moment. So this is all you need in your equations or anything. Yep.
Go over thrust again.
Yeah, thrust is just whether the two things can move along their axis or they can't. You know. So okay, so like right now, my two arms are sharing this pen is like a pin joint between them. You know, but there's nothing keeping this hand from sliding back and forth along the pin, and so that's no thrust. Whereas this one, I can't go right or left because these flanges hold these in place, and so that one provides thrust. Okay, it's a way cooler sounding word than what it does. It just keeps it from moving along the axis. Yeah.
So like in your example, it's those two different types of hinges then? Like you're not just.
That's right.
Like, because I guess I'm just trying to clarify, like it's not the same hinge and then you're just choosing to like include thrust for one in the free body diagram, but like not for the other.
Yeah,
They're
they would be two different joints. Yep. And I mean, like a door, I mean, you're using that door is using four of the same kind of hinges. So it's not, we just need to do that mathematically because otherwise we can't solve this stuff using statics. Okay, so joint category 6. So this is 3 force components and 3 couple components. So this eliminates all 6 degrees of freedom. The two things are just locked together. And this introduces 6 variables into the equations. Six variables into Newton's laws. And since Newton's second law and the rotational Newton's second law only give you 6 equations, that's the most variables you can solve for. So you can't, so if you have a thing that has, that's being held in place with a fixed joint and a cable and a pin joint, then you can't use statics to solve for those because that's, a lot of variables, 6 plus 1 plus 4 or whatever, you only have 6 equations and you have 11 variables. Okay, so this one looks like this or whatever. That beam there is just locked in place by a weld or glue or a bunch of fasteners. And a free body diagram of that body 1. I like when it makes that line straight for me. The free body diagram would look like this. So 1, 2, 3 force components. And 1, 2, 3 couple components. Okay, let's do an example problem. So let's say we have a big plate Bless you.
Thanks.
Okay, so you got this plate, and it's connected to the wall by a ball and socket joint. So, it's not very clear from that picture, but you just have to believe me that that's a ball and socket joint. And move this down a little. And then it's held in place also by two cables. So one goes, so we're going to go 2 meters here and 1.5 meters up on the wall. And so we have one cable that goes like this from the end. And then a second cable that goes 1 meter to the other side and 1 meter up. And that is connected to a second point by a cable. And this distance from the end to that second attachment point is 1/2 meter. And the distance from that second attachment point to the other end is 2 meters. So this whole thing is 2.5 meters long. And then the height is 1 meter. And the mass of this thing is 50 kilograms. And we want to know, what are the cable tensions? And the reactions at the joint. So can everybody make sense out of that drawing there? Those cables are both attached to the wall, the same wall that ball and socket joint is attached to. And I'm going to use a coordinate system so the first thing I'm going to do is just come up with coordinates for all these sort of key points in this problem. So I'm going to think of my coordinate system this way. Here's the x-axis, here's the y-axis, and here's the z-axis. And I'm going to label these points so we can find these locations. Well, the ball and socket joint is at the origin. I'm going to call this point, I'll call this point A, this point B, this point C, and this point D. Okay? And I guess we're also going to have to include the weight. So let's make the center of mass of this rectangle the point E. And so the first thing I'm going to do is just figure out the coordinates of those points. Okay? Notice that if I make my about point, when I get to calculating the moments and stuff, if I put my about point at the origin here, then the coordinates of all these points are also the row vectors where those forces are acting. Okay, so so in these sort of complicated problems where coming up with the coordinates is a little bit of a hassle, put your origin at the same place that you put your about point. Okay, it just makes you not have to do all the subtractions and stuff. Okay, so the point A, the coordinates are, you have to go I didn't label these. This is 1 meter, and this is 1 meter. So you have to go, to get from the origin to A, you have to go 1 meter in the positive Z, 1 meter in the positive Y. So this is 0, 1, 1. The point B, you have to go 2 meters in the negative Z, and then 1.5 in the positive Y. So 0, 1.5, negative 2. The point C, all you have to do is go 2 meters in the positive X. The point D, all you have to do is go a little farther in the positive X. So this is 2.500. And then finally, the center of mass, you have to go, so it's going to be, the whole thing has a length of 2.5. So it's going to be a distance of 1.25 along X. And then the height is 1, so it's going to be negative 0.5 along Y. And then 0 for Z. And now I'm going to draw the free body diagram. There's a weight force coming from the center of mass. That's 50 times 9.81, so 490.5. There is a cable going this way. I'll call that TB. And then from this point, there's a cable going in a different direction. I'll call that TA. And then the last place where the body makes contact with the surroundings is at the ball and socket joint. So now you can just go to the list of joints and see what kind of loads a ball and socket joint applies. But let's think about it for a second. So first, let's think about translations. Is translation restricted along the x-axis by the ball and socket? Yes. Along y? Yes. Along z? Yes, along z. All those translations are, that ball and socket just locks it in place. So like your hip is a ball and socket joint. It'd be bad if it allowed motion along any axis, you know? And now, what about rotations? Can it rotate about the x-axis? Yes. Y-axis, which would be like around this way? Yes. Z, which would be like a knife blade? Yes, that's allowed. So all we have is 3 force components. And that's what it says in your notes from last time. So I'm going to put this in as an unknown vector, and I'll call this R. And now, just like we did in 2D, I'm going to just write out this table. The only difference between the table in 2D and 3D is that in 3D, in general, none of the components are 0 on any of these vectors. So we got rho, force, moment. I'll start with R. And in red, I'm going to put my about point, which, like I said, I'm going to keep it at the origin. That's going to mean that forces that are applied at any of these points, A, B, C, D, E, their row vector is just going to be their coordinates that we already know. Because the row vector is from the about point to the point where the force is applied. So if your about point is the origin, that's always just the coordinates of where the force is applied. So R, what's the row vector?
0, 0, 0.
Yep, 0, 0, 0, 0. Force vector is Rx, Ry, Rz. Cross product is 0, 0, 0. Then I'll go for the weight force. The row vector, that's the point E, so the row vector is 1.25, negative 0.5, 0. The weight is 0, negative 490.5, 0. The cross product is so you can just plug these into your calculator. You also can go cross out the component you're calculating. This times this minus this times this. Remember that the y component, though, you have to add the negative sign. So anyways, this one has only a z component. And it is negative 613.125. And now we have to get to those cable forces. Okay, so now there's a little bit of work to do for those cable forces. What we have to do is figure out a unit vector in the direction of each one, each of those forces, and then multiply it by the variable. So for TA,
Wait, are we gonna be given the angle or not?
nope. In 3D, really, the angles don't mean much because you'd need them in multiple planes, you know? So what we're going to do instead is we're going to take, like for TA, we're going to take the coordinates of A minus the coordinates of C, and then calculate the unit vector in that direction, and then multiply by the variable. So the vector is A minus C. But this isn't a unit vector. So this is 0, 1, 1, minus 2, 0, 0. So that's negative 2, 1, 1. Then the unit vector my calculator will just do that with the unit v function. So that's negative 0.816, positive 0.408, positive 0.408. And so the force vector is negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. Okay, so for the force TA. The row vector is just the coordinates of C. So 2, 0, 0. The force vector is negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. And I'll take this cross product. I can just do it without the TAs on, and then I know all my components are multiplied by TA. It's like pulling a constant out of a multiplication. And so our moment vector is 0 for x, negative 0.816 TA for y, and positive 0.816 TA for z. Oh my gosh, we're over already. Let me just finish the table, and then I'll describe what to do, but we'll finish next time. So then TB well, let's finish next time.
I have a question.
Yeah.
Is there a way, you said you put the unit vector in your calculator?
Yeah.
Do you have a program for that on D2L?
It's probably on there somewhere, maybe in that textbook document.
Yeah.
Yeah, look in there and see if it is. But if you have an Inspire or an 89, it's a built-in function.
Oh, it's a built-in function?
Yeah, called unit V. And so anyways, now that once you have the table, add up all the vectors for F, set it equal to 0, add up all the vectors for M, set it equal to 0, just like in 2D. Okay, have a good weekend. I'll give you some homework to do.
And our homework is also emailing that